audience are all test, test, test. Testing, 1, 2, test, yeah. Clip that onto your...
Okay, for those of you who are watching remotely, just a few more minutes before we get started. There were a few minor technical difficulties getting the system up and running, Wi-Fi passwords. So we will be starting here within 5 to 10 minutes as soon as our director, Steve McVoy, gets back with the rest of the audience. So thank you.
I'm going to cut it. Okay. Well, here. I can cut it here. Chairs are self-service.
here in Hilliard today, we thought you might want to have a look at it. So don't miss it. It's right in the middle of the museum. Thanks for coming. That's hot now.
Yeah, the guy you worked with last year, I guess you heard quit unexpectedly.
I heard he got let go, but whatever.
Is that what happened?
I don't think, well, anyway, Mike's on, by the way.
Oh, okay. All right. This is sort of precarious. Well, I think we'll get started. Can everybody hear me? This one? Okay. Welcome to, I don't know which, can we start it in 2000, I guess? So this is the 23rd. No, we skipped a year or two because of COVID. But anyway, we've had more than 20 years of conventions. Want to welcome, we have a lot of new people this year. Out of our total attendance, which is going to be about the same as last year, I think we had 30 people who have never been to the convention before. I haven't met many of them, but I hope they're young because we certainly need young blood in this hobby. The lunch is going to follow this. It'll be set up just at any time, I think. So if people get hungry, you can probably, as soon as they're done, you can go grab something to eat if you want. But the live and silent auction will both start at 2 o'clock or thereabouts. We're a little behind schedule because of the catering issue. But they'll start around 2, and then live auction will last about an hour. Silent auction will go on until somewhere around 5, when we'll close it without warning to avoid people standing in front of bid sheets to keep their competitors from putting a last-minute bid in. Yeah, has been an issue in the past. So we have 2 presenters today. Both of them are well known to the collecting community. Matthew DeSaro is going to be starting and giving a presentation on his gadget, I'll call it, that he built a complicated gadget that he built to convert over-the-air digital signals to signals that can be watched on vintage TV sets. And then Mike Molnar will follow with his presentation about TV always being around the corner. And you'll see the history of TV in the early days. It's just, we're almost there. It's just, and you can see just magazine, newspaper articles about television is here, or television will be here tomorrow. Along with a few skeptical comments too. I imagine Mike will be talking about that. As a matter of fact, television took a long time to actually get off the ground. But anyway, I'll leave it to you people. I have to go back and work on the auction, but have a great convention, and we'll see you over at the museum after lunch. Thank you. Yeah. Oh, yeah, how about that? That would be interesting. You'd hear some interesting conversations.
Thank you so much to Steve McVoy for all he has done for this convention and this community, and for the warm welcome to me as our first presenter. Thank you all very much for coming. I'm excited to be here, as I'm sure you are all as well. And then, without further ado, let us begin discussing my almost 10-year-long, well, more like 5-year-long effort to develop a what amounts to a private cable TV or community access television headend to allow vintage television sets to receive all of the local stations, in my case in Seattle, but could be anywhere, as they would have originally. Before I jump into this, just a quick little bit of fun history on cable TV. As what we know as cable TV, or CATV, was originally community antenna television, because from the very beginning, people would live in valleys, and they didn't want to move to hilltops just to receive television. So a group of residents would get together and each chip in some amount of money to maintain a antenna system, much like this more modern system I have shown here, consisting of an antenna, some amplifiers, and sometimes filters, and then a feed to television. So it was only later that the content on cable was different from what you had on the air, and also just pointing out that the idea of not putting rabbit ears or an antenna directly on top of a TV, but rather feeding it from a remote antenna actually dates back really to nearly the beginning of electronic television. So with that, I will get into the motivation for this project. So growing up in Seattle, in a valley by Lake Washington, did not have direct line of sight to any of the television receivers. So from the time I was a little kid, television we had always came from a cable, not from an antenna. We tried, when I was a small child, to set up an antenna on the roof, and it did not go very well. Got a very ghosted picture, which sort of maybe you could make out. So we watched, I think, the 2000 Olympics, if I'm remembering right, on an over-the-air signal, but it never really worked. And then when 2009 came along and the digital transition occurred, naturally there was no more NTSC over-the-air broadcasts, but I had high hopes that the ATSC, or Advanced Television Standards Commission, the current US television standard, ATSC 3 or Next Gen excluded, would allow us to receive television at my home. Similarly, during that time, prior to the transition, immediately after, we received analog cable TV. So we received an actual television signal, NTSC format, over a piece of cable that came into the house. And from the time I was a little kid, I've been interested in analog televisions. And of course, I would plug in the cable and it would mostly work, although not understanding about adjacent channel interference, get a little bit of a herringbone pattern. So the bottom line is that in this modern digital age, antique radios, amazingly, still work as originally intended. They receive the current over-the-air programming, as they always have for over 100 years. This is a 1921 Westinghouse RC, arguably the very first radio sold for consumer use. And they can be tuned using their own tuners to select among present-day radio programs. Antique televisions, on the other hand, or vintage televisions, do not work as intended. You cannot simply place it on a table, put up the antennas, and get a picture. It cannot receive over-the-air programming without an external converter. And the standard digital television converter box that you can get will allow a vintage set to receive over-the-air content, but not really as originally intended. After all, you're just using the tuner of the TV to get one channel, and the converter box itself is doing the the tuning for you. So my motivation here with this project, and had been since the digital transition in 2009, was to find a way to build my own converter of some kind. It ended up being essentially a private cable TV head end that would allow me to receive locally in my home all of the local television stations on my vintage sets and enable my vintage TVs to work as originally intended, i.e. to be able to flip through the channels with their own tuners and get a clear picture. So specifically, the goals of the project are and were to allow vintage TVs and even vintage UHF converters, those useless boxes that show up at events like this, to work as intended again. So without, just as if you had a community access antenna and you just wanted to plug that in and receive TV. That was the goal. Be able to create the wow for viewers of my collection by turning on a vintage set and going clunk, clunk, clunk with the original tuner and seeing the local stations come in. For those of you who like to use your sets as a party trick, for people who know just enough, that always gets a, how did you do that moment? I wanted to create a channel plan that mimics what would have historically been in my area. One, well, I don't think we ever quite had channel 1, but 2, every other channel except where there's gaps in the plan. So, 2, 4, there's a gap, 5, 7, 9, 11, 13, because the skirts of the IFs in old TVs are not sharp enough to be able to separate out adjacent channels. That was what cable ready meant. Much later was that they had typically a surface acoustic wave filter that could separate out adjacent NTSC channels. So that was the goal. And as I said earlier, having no adjacent channels was not a feature of most 90s and 2000s analog cable systems. So if you hooked it up to an old TV, you'd always sort of be fussing with the fine tuning knob to try to get rid of the herringboning pattern. So wanted to fix that. I wanted to include the short-lived channel 1 for my Motorola VT71 and my 621 TS, two sets with the channel 1 on it. And I'll talk a little bit about attempting to include the most modern form of television reception, which is streaming, which is, those of you who are watching remotely, is in fact what you're using. So I wanted to see how I could get streaming onto vintage sets. All right. So we're going to work through the rest of this presentation from one end of the system to the other. And the first part of a community access television system is the antenna, because television is a form of radio, receives signals over the air. Not all of this would be applicable to every installation. Obviously, antennas, very specific to where you are, what works best. But given the challenging reception environment that I'm in, I ended up having to have a fairly complicated antenna system in order to get clear reception on all of my local ATSC stations. Specifically, where I'm at, UHF, which is this antenna here, a Channel Master Extreme 1080, which, having tested a very large number of different UHF antennas, I will insist is the best choice that I've found currently available. That's for UHF, which in my locale is actually best received as a bounce off the lake. I was not able to really get line of sight because of foliage and terrain in between. On the other hand, VHF refracts enough around the terrain and isn't attenuated enough by the vegetation that I am able to get line of sight VHF, and that works better than trying to get that as a bounce. So I have a separate VHF antenna, Stellar Labs, also known as MCM Electronics. There's the model number. This is all on YouTube. You can ask me later. But this is a VHF-only antenna, and that's important. I'm trying to avoid multipath here, which I'll talk about in a minute. So VHF only, UHF only. And then I'm combining the two antennas together into one feed using what's known as a diplexer. And what this is two carefully tuned filters, which will allow only VHF signals from the VHF antenna to get into the feed line, and only UHF signals from the UHF antenna. What that avoids is a multipath interference problem, where if you have two antennas receiving the same station from different paths, there's going to be different delays on those two paths, and therefore you'll get multipath interference. I'll talk more about that in a minute. So the schematic so far is we've got VHF coming in this antenna, UHF coming in this antenna. They're coming together at the base of the UHF antenna mast in a diplexer. So the next piece of the system is an antenna preamplifier. Now, there's a lot of confusion among people who not so experienced with setting up television antennas of the purpose of the preamplifier. To put it very simply, the purpose of the preamplifier is to overcome the loss in the feed line. That's it. It's not going to remove noise that is on top of your signal itself. It's just an amplifier. However, it can add noise. In fact, all amplifiers add noise. The noise figure is a number in decibels, which specifies how much noise an amplifier is adding to the existing signal. So the most important parameter in an antenna preamplifier is that noise figure. You want that to be very low. Now, in my particular area, I actually have plenty strong signals, not way out in the country. It's the multipath interference that gets me. So I was actually slightly less worried about the noise figure here. But I did want that to be minimal. The thing that is important is not to use too much gain, because if you use too much gain, you'll overload the preamplifier and you'll get what's known as intermodulation distortion. And that's where, just like in the mixer of a radio, when you have a non-linear electronic element with two different frequencies entering it, i.e. two different channels, you'll get the sum and difference frequencies out. So you'll have ghost channels appearing where they shouldn't be on your spectrum and interfering with others because of intermodulation distortion. So make sure the gain is sufficiently low, get a low noise figure, and in this particular installation, I added an LTE filter. There are some, with the DTV transition, some of the old television band was reallocated for cell phone use, so blocking that out will help prevent overload of the antenna if there happens to be a cell phone or a cell phone tower nearby. This is the model of amplifier I used. Set some switches inside to set the gain, turn on the FM trap, installed the LTE filter, and that's pretty much it. The one thing I'm going to mention here is I mounted the preamplifier on the UHF antenna mast next to the diplexer. If I was very worried about signal strength and wanted to make sure to overcome the loss in the feed line from the VHF antenna to the diplexer, I could have had a second preamplifier there, but measuring those signal strengths with the spectrum analyzer, I had plenty of signal strength. It was not necessary. Only really the UHF on the bounce was near the limit of signal strength. So I just have one preamp in this system. All right, so from here, we're up on the antenna. We're going to follow the feed line down to the utility room where the start of the head end system, which is the big rack of electronics on the first slide, is set up. The first piece of that head end that the antenna signal encounters is the antenna signal distribution amplifier. The purpose of this amplifier is to overcome the loss in the splitter. We have to take this one antenna signal and split it, in this case, 16 different ways. So recall that 3 dB is half power. So if you had a theoretically ideal splitter, you'd lose 3 dB for going two directions. But in reality, because of impedance matching, it's worse than that. So you actually need quite a bit of gain just to overcome splitting the signal 16 ways. There are many devices that are sold as cable TV distribution amplifiers, which are just amplifiers, power amplifiers that are wide enough band to cover the whole antenna or cable TV spectrum. They also sell splitters, but devices that combine an amplifier followed by a splitter is somewhat hard to find. Basically, I would have to have had a separate splitter and a separate amplifier, and sort of short of rack space for the cooling needs. So I ended up actually modifying a Drake AC 1686, which is what's known as an active combiner. It's made to do the opposite. It's made to take 16 modulators, and I'll get to what that means in a minute, combine them together into one signal with a power amp to overcome the loss in the combiner, because it turns out that combining and splitting are really the same operation, and they have the same, you get the same loss through the splitter. So it was simple to do this modification. All I had to do was take the cover off of the active combiner. That's this box here. It's opened up. This is the power supply. This is the actual splitter combiner. It's laid out on this circuit board behind the F connector jacks. And then this is the amplifier. So all I did was add these tan cables here to just connect the amplifier to the, flip its in and its out, so that it was designed to accept a signal into the amplifier and then split it 16 ways, as opposed to taking 16 signals, put them together and amplify it. So just a couple of F connectors, super easy. I rebranded the front of this as AS 1686 with a little label maker, just as just for fun, as an active splitter instead of active combiner. The thing to keep in mind here with anytime you're amplifying a power amplifier, or really any amplifier in a system like this, is that it's important to set the gain correctly to avoid overloading the amplifier. So looking at the total power output with a power meter, or adding up the powers of each channel using a spectrum analyzer to make sure that we don't get that intermodulation distortion, which is a real problem. So I ended up using an RF power meter to assure that I got unity gain. In other words, the same amount of power going in, going in comes out each port, and did the math per the data sheet to make sure that that was below the power limit to achieve the intermodulation distortion that I needed. Again, noise figure is less important because it's always the first amplifier in the chain that's most critical for noise figure. We've already amplified this with a preamplifier, so you want a low noise figure, but it's not nearly as important as the preamp. All right, so now we've distributed the signal. So we have antenna, comes down, antenna, preamplifier comes down the feed line, gets distributed 16 ways. Now we have to take that digital signal and we need to demodulate it. So in this case, demodulate doesn't quite mean just, shift with a heterodyne and filter out the channel you want, because it's digital. So in this case, when I say demodulate, I actually mean, yes, demodulate, bring the single sideband ATSC signal down to baseband, but also decode, digitally decode, to give us back a baseband NTSC signal. Okay, so we're doing the digital to analog conversion step in the demodulator. So your common DTV converter box, which I'm sure all of us are familiar with, would be an example of an ATSC demodulator. So this takes ATSC, gives us NTSC out the other side. I will contest the term that the cable TV equipment suppliers use as referring to a digital to analog converter as a demodulator, but that's the terminology that they use in their data sheet, so I will continue. The DTT 901, by the way, widely available on, no longer made, but widely available on eBay and the like, is just about the best performing ATSC demodulator I have found, having tested just about all of them. So the purpose, again, of the demodulator is to tune in to a single ATSC channel, demodulate to digital baseband, decode that digital baseband to video, and then modulate, well, not really modulate, but decode that digital video and encode it with a digital to analog converter as NTSC. You'll also see ATSC demodulators which put out digital formats such as ASI, asynchronous serial interface, which is a way of sending digital signals around inside a cable TV system, or some other digital format. But in this case, we're referring to ones that give us baseband NTSC. in this whole system, the ATSC demodulators are the most critical part. As I said, where I'm at, I have a really hard time receiving ATSC. There's supposed to be improvements with ATSC3 that reduce the effects of multipath interference, but as it stands now, it's quite a problem. So the basic idea of multipath is if we have one transmitting antenna and one receiving antenna with a hill or something nearby, we can have one direct path from the transmit antenna to the RX antenna, and then one or more, sometimes many, indirect paths where it comes off the transmitting antenna, bounces off the hill or a building or a lake, whatever there is that would be in between the two antennas, and then be received as the RX antenna. And you can see the path lengths are different. The indirect path is longer, which means there's a phase shift in the received signal. You get two copies of the same signal, time shifted, but on top of each other. And that makes it very difficult for the ATSC demodulators to demodulate, to decode the digital signal. The way this is corrected is with a filter that's called an adaptive equalization filter. And the way this works, it's a digital filter, and you can imagine conceptually having a delay line and tapping that delay line to pick a specific delay, and then having many such delay lines and adding up the sums, each with an appropriate weight. And if you do that, that's exactly the opposite of what happens here, where we have different weights of different delays, and so you can cancel out the effect of the multipath and give you a clean signal that can be easily demodulated. But the algorithms to figure out where those taps should be and what the gain of each of those taps should be is not trivial. And so there's been a lot of improvement, a lot of variation between vendors of those demodulators. So, as I said in my testing, the good old-fashioned Zenith DTT 901 performed just about the best, but it's not a rack mount unit. It's difficult. Whenever you try to do 16 of something, it gets pretty difficult to program everything correctly if it's not made to be used in a rack mount system to cool everything correctly. So I wanted to use professional cable TV, CATV equipment for this. So I ended up trying several different brands of rack mount ATSC demodulators. So this is the first one I used. This is the Blonder Tongue AQD system. It was introduced in about 2006, right when ATSC was starting to come on the air, at least in an experimental sense. I don't know that date exactly, but it's somewhere in that ballpark based on the date codes on parts and on boards. It's very early, runs very hot because of the limited, lower tech electronics available at the time. And I had very poor reliability with these. I actually had 3 or 4 of them fail in my system or were failed when I bought these used. I'm not buying it new, it's horribly expensive. I'm an electronics engineer. I work on circuit board design for a living, so of course I get curious what the actual failure mode is. Turns out that it's this chip here, which is an ASIC, or application-specific integrated circuit, which is used by the demodulator to do the actual digital decoding. What happens with these is that the plastic part of the chip that you see gets hot, and the board underneath it less so. And there's a whole array, tiny little array of balls or blobs of solder, called solder balls technically, underneath this chip, which make all the connections. So if you have a different thermal expansion coefficient of the plastic part and the board part, the two of them will strain against each other every time it heats and cools, and that will eventually crack the solder balls. So I was actually able to fix a few of these AQD boards by removing those chips. I found some replacements in China and soldered them on, but it was not very reliable. They run hot. They did not receive very well in my area at all. It was a real struggle just to get all the local channels to come in at all. And it's pretty hard to configure. It uses this little control box with little arrow buttons, and it's pretty primitive. I also tested the newer, so the AQD system's been discontinued. Blonder Tongue still sells a version of their MDDA system, which allows you to fit more of these modules in the rack. It's only a 2U instead of a 3U tall rack. Widely improved, but unfortunately still uses this same or very similar ASIC, so I did not see any improvement in the adaptive equalizer. So I was still having a very hard time receiving all the local stations. So that was my first attempt. I got that done in late 2017, right after coming home from living out in Boston. Ran it for a bunch of years, and then in 2020 decided that I really wanted to upgrade. I had had enough of these Blonder Tongue AQD modules fail. I wanted something better. So after doing a lot of research, I ended up settling on the Drake DAD 860s. The adaptive filters are not quite as good as the Zenith, but they perform much, much better than the Blonder Tongue AQD. Get a stable picture pretty much all the time from turn on. It does not use failure-prone capacitors. There are electrolytic capacitors here, but they're all good quality and they're all through-hole, not those horrible little surface mount ones that always seem to leak their guts out. I found them to be robust and reliable. They do still have a large ball grid array ASIC in them, but it doesn't run as hot. And I think they've gotten the solder tech improved a bit. These are from more like 2010. And best of all, it has a serial port on the front of each unit. You can see them here. That's the little silver connector. And those plug into any Windows computer. So you can program the channels manually from this very nice little Windows GUI. You can set the frequencies, you can manually add a channel, you can set up a configuration file for your local area and copy it to all of these. So way, way easier to deal with than the Blonder Tongue ones, and even easier still than the home boxes. So really a very nice system. The other nice thing about this is, I don't know if you can see, but these same racks, on the left here there's a controller module, which is two of these little mini units wide. And then there's a power supply on the right, and the power supply will drive both these DAD 860 demodulators as well as the VMM 860AS modulator. So I could go demod, mod, demod, mod, demod, mod, which avoids a lot of long cables running from one big rack mount unit to the next. So a nicer system all around. I'll also point out that there is a Pico Macom MPD, which is also a rack mount system, uses the same form factor, different control box, that's proprietary. I don't own one, I'd like to, but I couldn't find any inexpensively on the used market when I was setting this up. The challenge, I have not been a huge fan of Pico Macom CATV equipment. I prefer Blonder Tongue and Drake, but both US companies, Pico Macom's Taiwanese. But the Pico Macom units are newer. They might have a better adaptive filter. So that's just a heads up if you're building something similar. You should probably compare those to the others in your area. All right, so having settled on a demodulator, the Drakes, the next thing was to figure out how to do the aspect ratio. So one of the most frustrating things about trying to use vintage sets with modern content is that modern content's designed for a different aspect ratio, a 16:9 aspect ratio as opposed to a 4:3 aspect ratio. Also, modern TVs do not trim the edges of the picture as vintage sets do. So between both of those, you got to do some sort of scaling to get this to work. And there's no perfect option here. Fundamentally, you can't simultaneously see all of the picture and not have some distortion or black bars. So the choices are, we can stretch the picture, which distorts a 16:9 picture to fit in a 4:3 screen. This is just plain a bad idea. Don't do it. Also, we'll comment that if you have 4:3 content, which was broadcast with black bars, and you squish it, now you have squashed 4:3 content, which still has black bars. So, no. The next choice is letterbox. This is what most demodulators default to. That's where you put black bars on the top and the bottom so that you see most of the 16:9 picture. Notice the mask on your vintage set is still going to cut off the edges, and therefore you're still going to lose something on the sides, even with the letterbox option. A few things that are troublesome with vintage sets. Vintage TVs were not really set up to have very large contrast gradients horizontally across the picture. Some of the more primitive sync circuits can get a little bit confused on those black bars. I see some of the audience members nodding, you know what I'm talking about. So that can be an issue. It also makes 4:3 content, which was broadcast with black bars on the sides, now be a small picture with a black frame around it, which just looks really dumb, sorry too. But it really does not look like a good look for the vintage set. So honestly, as much as I sort of hate to cut off part of the picture, the best option is to crop it. Just to crop everything. Because for the most part, you know, if you're going to lose being able to read some of the text on the edges of the screen, you're probably going to lose that anyway, even if you do your black bars because of the masking on some of your sets. And for demoing the TVs, it just looks a lot better to have a full screen picture. And for most content, you know, you have a politician talking, you have the, you have your TV show. The center of the screen is where the action's at anyway. So just cropping the edges off works the best in my experience. The last option is a feature called AFD, Automatic Format Detection, which uses codes that are broadcast with some programs to automatically decide between letterbox and crop. In principle, this is a great idea and sort of solves the format problem. The reality is that in this day and age, the TV stations are so disinterested in 4:3 users that the AFD codes are usually meaningless.
Common issue I've seen is that they're broadcasting a vintage show that was originally 4:3. They'll stick text or graphics on where the black bars would be and transmit it as 16:9. So
Yeah.
you have to crop it to make it look right.
Exactly. So I tried AFD. I was really hopeful. I found it a waste of time. So go with crop, my recommendation. All right, so we've got our antennas, our preamplifiers, our distribution amplifiers, our demodulators. Now we need to modulate because the whole goal is to get this on vintage sets. So this is the fun part. There are many models of NTSC modulators available. Unlike the demodulators, it's a pretty standard thing. Every cable TV system had them. I'm not going to be able to go through all the options here, but I'll go through some of the main differences between models. The first point to realize here is fixed channel versus frequency agile. So fixed channel modulators would be what would have commonly been used in older cable TV head-end systems. Each one has a SAR filter in it that's tuned for exactly one channel. And a crystal, you get what you get. They're less expensive, they take less power. Because of the custom tuned SAR filters, they typically, I think always, but not totally sure, I haven't looked at all the models, produce true vestigial sideband NTSC. I'm not going to go into the technical details of what that means, but it's a true, perfect broadcast quality NTSC signal. They're hard to find in the desirable VHF channels because most cable TV systems, most of the channels were higher than that, and the VHF ones are in demand. And it's inconvenient not to be able to retune your system. It's really sort of a pain. So I recommend using agile modulators, which are more expensive, depending on the model, may or may not produce true vestigial sideband NTSC, not that I think we really care for the most part with vintage sets, but they're much more versatile and convenient. Next thing to keep in mind is the physical size. The older models were typically 1U per channel, which if you're trying to put this in a compact space, gets very large very fast. The newer units, like the demodulators we were looking at earlier, allow 12 modulators per 2U. So I prefer that newer form factor. Stereo or mono sound. As far as I know, there's not really many problems with using stereo sound with that sub-carry-on vintage sets, so I opted for it just so my 90s sets would get true stereo, which is kind of fun. So specifically, I've used both Blonder Tongue ACM 806. The 806 is the highest frequency that it will transmit way high in the UHF, where again, we're not that interested in typically as vintage enthusiasts. And the Drake VMM 860. Both work fine. I found that the Blonder Tongue units did not require recapping of all the SMD capacitors, while the Drake units did. However, once recapped, the Drake units were actually more reliable, quite a bit more reliable than the Blonder Tongues. I had several failures in the Blonder Tongue units. May have been due to inadequate cooling on my part, plus the units were used when I got them, so take that with a grain of salt, but both are good quality. I'll just point out that there are 5 surface mount capacitors that need to be replaced for long-term reliable operation in the Drakes. Before you do that, video or audio was weak on some of them. Others, the digital display wasn't quite right. But you just replace those capacitors. I mean, if you're good at capacitor replacement, it's not that hard. And these will come right back to life. All right, so after the modulators, we have the amplified or active in the CATV speak combiner. And again, this is so that you can overcome the loss due to the splitter combiner, which inherently has loss, in order to maintain impedance matching, so-called magic T. So the purpose of this is to overcome that loss in the signal combiner so that you get the correct amplitude, sufficient amplitude of each of your channels out on your final cable TV system. Again, there are many, many models available. I was trying to build this system up as pretty much a fully Drake system. So I used a Drake AC1686, same model I modified to make the active splitter. Again, the big issue here is intermodulation distortion, just like on the antenna side. But here, because it's an analog signal, it's not masked at all. So you'll see it on the TV sets. So basically, if you have excessive intermodulation distortion, you'll see a weaker version of some channels will appear mixed up and offset in between other channels. Ghosting, herringboning, that type of thing will start to show up. Not good. The important spec to look for in the data sheet is IP3, the third order intercept point. Again, I'm not going to go into the technical detail of what that means. It basically, lower numbers better. I'd say a good power amp should be negative 60 dB or so on this IP3 point. And again, really critical that that gain be adjusted correctly to assure that the amplifier is not overloaded per the maximum output spec. Basically, if you can get 1-to-1, so the same amount of power coming out of your modulator that's coming out after the active combiner, you should be set correctly. You can see that with a spectrum analyzer. The thing to note here is the specification, the data sheets for the maximum output can be rather confusing, as it's usually given as a signal level in dB microvolts or dB millivolts for a channel, for any given channel. But in reality, what matters is the total power, which would be the sum of the powers in the individual channels. Because of the dB units, you have to be a little careful with that. So just recall that if you double the power, that doesn't mean you add the dBs. That means for every doubling, you get 3 dB. That's how logarithms work. So just you have to pay a little bit of attention to make sure that you're not exceeding that maximum power output. Very, very important. All right. Recall one of my goals was to recreate the famous Channel 1. It turns out that there is one specific model of blonder tongue agile modulator, which is sophisticated enough, or maybe not sophisticated enough, that it allows you to tune the various stages of the modulator, tune the frequency of the various stages of the modulator manually with a set of dip switches. And because of this, some smart people, who were not me, figured out how to adjust those dip switches to program it to be exactly the right frequency for the historic Channel 1. So the key thing here is that you want a blonder tongue AM series modulator, but it has to not have an LED display. If it has an LED display, it won't have the dip switches and it won't work for this. There were multiple different models of the so-called AM series made. The first number is a power output spec, so the 40 puts out less power than the 60. Don't really care, frankly. And the second number is the maximum output frequency, so basically the highest channel, so 450 megahertz or 550 megahertz. Any of those will work fine for this application, but again, can't have an LED display and it has to be a blonder tongue AM. There are other modulators out there with dip switches, but most of them that I've seen, and if someone knows of another one this will work with, I'll be all ears, but most of them, the dip switches just sort of set a channel number. They don't actually let you tune the frequency of each stage of the modulator separately, so you can't hack them in this way. The next thing to keep in mind is that if you're going to put Channel 1 on a cable private cable system like this, it needs to be on its own switch. And that's because a lot of modern 1970s and newer solid-state TVs with UHF use a frequency for the UHF intermediate frequency, which is very similar, well, to the old channel 1 frequency. So what you'll get is a whole bunch of nasty herringboning all over your picture on some unrelated channel when you have your channel 1 modulator on. So you just need to make sure that when you're demoing a newer TV, you turn off your channel 1 modulator and only turn it on when you actually are demoing a channel 1 set. So a little annoying. I was sort of hoping I could leave it on all the time and just have it be there, but not technically part of the channel plan. And then the next comment I'm going to make here, just real quick, I didn't want to dedicate an entire local channel just to channel 1 because 90% of my sets couldn't even receive that. So I just wanted to split one of the local channels. Historically, channel 1 was typically used for like educational or local programming. So I picked the local lower power, my area, channel 19, UHF station to use for this. And I wanted to send that one station out, both a UHF modulator, a standard little rack mount NTSC modulator, as well as channel 1. But to do that, I had to do a couple of things. First off, I had to have a splitter for the video signal. Remember, video signal is 6 megahertz wide. It's, it's RF in its own right. And I wanted the same video level going into both modulators so that that channel wouldn't have a, weaker video signal. I tried turning up the gain to compensate and ended up deciding it made more sense to use an active video amplifier splitter. So I actually designed this little board here on the right, which the one on the left. You can sort of see, looks like that. That just takes one demodulator video output on an F connector and amplifies it and splits it in impedance matched manner, so you get the correct 75 ohm output impedance on two paths. So one again goes to the modulator for the UHF channel and one for the channel 1 modulator. Similarly, for the audio, the channel 1 modulator, these Blonder Tongue AM series typically are not found with the stereo option, and frankly, stereo sound on channel 1 makes no sense. So I wanted a mixer that would mix down the stereo audio to mono without do that in a technically correct way so that you wouldn't overload the amplifier drivers on the on the driving circuit. So you could just use a resistor divider. I ended up using a little op-amp circuit. That's what this one on the right is here, and you can see that hooked up right here. So I just used RCA splitters to split the audio, and then this is a high impedance input here and then a down mixer. So mixes the stereo down to mono. Very nice little board, and these can be powered. You can see here off of the same power 12 volt and 5 volt power cables that are powering everything else in the system. So I just made a little splitter cable there to do that. All right, so that was channel 1. A lot of fun, kind of a gimmick, but kind of fun to see channel 1 work. The next thing was channel streaming. I'm going to keep this real brief. I was not able to make this work very well. I set up a sync detect video switch to switch over my channel 3 between channel 3 over the air, that demodulator, and a Roku streaming box when I remotely turned on the Roku box, which you can do over Wi-Fi these days. That part worked. It was really cool because I could take my phone and I could open up the Roku app, and even though my cable TV system's down in the basement and the collection's upstairs, I could do the Roku from my phone, and so it would show up on the vintage sets. The problem is that the Roku really has very, very poor support for 4:3. It likes to make a distorted, squashed picture for many video sources. The menu is not designed for a 4:3 screen and can be very hard to navigate. And yes, I'm setting the menu setting inside the Roku to 4:3. Also, just the quality of the NTSC video that it produces isn't great. Unlike some older devices that I have had in the past that used to work with streaming services like a Nintendo Wii or the old versions of the Roku that no longer will connect because they've been obsoleted, the video output was just not great. Also, the Roku Express Plus has been discontinued, and neither Roku nor anyone else actually makes a streaming box that will put out composite NTSC video. The right solution here eventually will be to build a better HDMI to composite adapter that will downscale 1080p to 4:3, do the cropping, all of that, but I also have a full-time job and a girlfriend, so I have not designed that yet. When I do, that will be a presentation here, I promise. But for now, streaming works, but sort of so-so. Some other important considerations here that I didn't touch on in detail. Cooling is critical. My first rack built out of Blondertongue parts, I did not have enough fans in there, and it really ran hot up near the limit, the temperature operating limit that the datasheet specified, or above it. That probably contributed to the premature failure on some of my units. As I said, I've seen some fail even, used in commercial environments, so not the whole story, but definitely part of it. You can see here in my current system with the Drakes, I'm using these little 1U fan boxes that blow air in between each section of the rack. That helps a lot. I also put a cooling fan in the room, exhaust fan that circulates air to make sure that the utility closet that this is set up in doesn't get too hot, and that fan kicks on when I turn on this system. I set up remote control switches, which allows the system to be shut off remotely when not in use to just save on electricity and runtime on the equipment. Power conditioning is important. You got a lot of expensive electronics in a rack. Surge protector, good idea. All the signal distribution and all the wiring, plumbing, as I joked, with these little F connectors and these stiff cables, really important to get clean signals on your NTSC channels without the TV accidentally picking up ATSC that's broadcast on the same frequencies. Copper braid cable is the best, but really expensive per foot. I found that the quad shield is almost as good and reasonably inexpensive, but don't use cheap cable. Buy from Belden specific CATV quad shield cable, and always use compression connectors. That's the kind where you stick the pin in there, and you have a special tool that squashes the two ends together, makes a watertight seal. Very, very important. Then another little demo. Leviton actually makes these nice little outlets, which have cable TV outlets that have 2 jacks on them. So I have one that's labeled antenna, is coming out of my private system, and that's for the NTSC output, and then the cable is just our Comcast cable. So we can have both for the new TV. Finally, a cable TV spectrum analyzer, defined by having a 75 ohm input instead of a laboratory spectrum analyzer that would have a 50 ohm input, is very useful for tracking things down. So good thing to invest in if you're doing something similar. This is mostly for those of you who are going to want to get the slides afterwards. You can study this, but this is a block diagram of my system. We have the VHF and the UHF antenna connect to the diplexer. There's the LTE filter, notches out the LTE. There's the antenna preamp. This is the amplified splitter for the antenna system. The 16 demodulators, the 16 modulators, the audio mixer, and the video amp and splitter split off the video and audio from one of those ATSC demodulators to go to the channel 1 modulator, and then the 17 signals go into an amplified combiner down here, which gives out NTSC. So that's the diagram. Again, some things are not shown, but for the sake of one slide. Finally, here is a photo of the converter system as set up. This is our utility room where we have our hot water and heat equipment as well. You can see at the very bottom of the screen here, this is my spectrum analyzer for testing. It's currently hooked up to the test point on the antenna distribution amp. I have 3 Wi-Fi switches here that allow me to turn off the whole system power, the Roku, and the channel 1 so that I can remotely control this. We have the 16-channel combiner and amplifier. This is the so-called active combiner. We have the modulator for channel 1 right here. Then we've got the 16 ATSC demodulators and NTSC modulators along with their power supplies and controllers. So that's the main bulk of the rack. And you saw close-ups of those earlier. Those are the Drakes. We have the antenna signal power amplifier and splitter. This is the so-called active splitter. Up here, a surge protector and power strip. This is the Roku and video switch box, and I am using this is the very first TV I ever personally owned. It was my TV. It's a 1980s Freedom brand made in Korea, black and white TV. Very convenient to have on the system for testing as you're tuning everything up. All right, so without further ado, here we have examples of live shots off of various vintage sets on this, on my system. Here is my 1949 Admiral. You can see this is a news broadcast. You lose a little bit of the text because of the cropping, but the picture is otherwise nicely framed and very clear. Here's a news broadcast on a 57 GE. That's the famous 9T001, the one with the CRTs that always go soft, so it's a little soft picture, and a 56 Emerson. The picture's not really distorted. The camera was a little bit off angle. This is my 47 Motorola VT71. Here's a 85 Casio LCD. To get this shot, I actually just touched the antenna to one of the to a live cable because it doesn't have a remote antenna input. And just to give you an idea here of the what this set's able to do, this is a modern 1999 Toshiba, all recapped, and you can see it's a very bright, clear color picture. So very little interference, looks digital. A lot of fun, really enjoy this. I think it adds tremendously to my vintage TV collection, and I would encourage those of you who are like-minded to please reach out to me for help in building something similar. I can provide additional details, schematics for the boards I built, model numbers, etc. Please contact me through my website at desarodesigns.com. That's my consulting business logo. And last but not least, here is a link to a very long album of photos. I'd like to thank my dear mother very much for helping me with the photo archiving and photography through all of this. This is to you, Dana, and thank you to Kayla, my girlfriend, very much for helping me out with this presentation and tolerating my TV collection. So same goes to Mom and Dad. A lot of it's just at their house as well. So without further ado, are there any questions?
How far are you from the TV transmitters, point to point from the transmission?
Good question. We're only about 10 miles, I think roughly, from my house to the Capitol Hill, where the transmitters are. Might be a little more than that. I'd have to look on a map to give you an exact number, but it's not that far. The big issue is Seattle's very hilly, and there's multiple layers of terrain between them and us. Question in the back.
Yeah, the cropping takes
Yes.
place in the demodulator ASIC, that's setting on it?
Yes, so the demodulator handles the cropping internally. There's a setting you can use through the little menu on the control box or through the Windows application. It will handle that in its ASIC. Questions?
On the modulators.
Yes.
Are you finding any HRC type stills out there? By HRC, I'm referring to harmonically related carriers.
They certainly exist out there. That's a good point. I've tended to avoid them and go for ones that can be programmed for broadcast. For the most part, the agile ones can be programmed for the various cable TV frequency plans as well as the broadcast plan, so that can work. I know there were some that were only the HRC.
That was the first cable system I worked for. We built it at HRC to prevent composite triple beat.
Yep.
Also, if you're looking for a inexpensive demodulator to go from HDMI to composite video and audio, there's one at, believe it or not, Walmart online.
Yes,
And
I'm aware.
the only thing it requires is an external 5-volt power supply.
Yeah, I'm aware that I have that unit along with several others. At least in this, it's changed in the last few years. It does not handle the aspect ratios terribly well. Question in the back.
Do they have to
No, I've been following that very closely. And someone here may know more, but I'm aware that the ATSC1 is still the FCC mandated standard, and I don't know of a hard date. Again, you may have a better answer.
Well, that's a good question. So I think broadcasters would very much like to shut off 1.0 at some point. The FCC about 2 weeks ago at NAB announced they're going to start studying that question. So it's probably 5 to 10 years away when 1.0 goes away.
Thank you. Question?
You have 16 ATSC modulators.
Yes.
Do you have 16 basic channels with all their sub-channels, or do you have like 3 or 4 stations and you're encoding all the sub-channels?
Very good question. In the interest of time, I'm going to avoid going through the whole plan, but the short answer is I have all but 2 of those are actual local base stations transmitting their base content. The last couple are sub-channels that are particularly desirable.
Okay.
Any other questions? All right, I will like to thank all of you again for being a wonderful audience, and welcome Mike up for his presentation.
Let me come around. Can't see. Blind as a bat. Okay. Here we go. Oh. That was a really great high energy, high power, high tech presentation for Matt. I'm going to come at it from the opposite angle with a slow, low tech presentation about when television was just around the corner. And that's, if you've looked at the mechanical room or some of the displays at the museum, you know that we just didn't start out with CRT television. Let me get my clicker worked out here. So, when there we go. Throughout history, there was a desire for seeing at a distance, and it was really just a dream. Is this early picture of correspondence cinema phonotelegraphique, like an early version of a dream of video dating. And then as the 20s came along, radio news even picked up on the idea that television would be ready for getting closer and closer. As the early days of radio, the dream of adding a television image receiver to the audio sets that they were using really gave the idea to people that television was just around the corner. Surely the big screen even was coming, and with that you can see even big commercials on the TV. There's also a dream of seeing from all angles, like a precursor to a 3D television. And soon television will make you a spectator even at the news events of the day. You can see he's got a remote control for the camera on the rooftop of his truck there. And who wouldn't want to record and play back their favorite programs right on a phonograph disc? And there were methods of recording some images. There was a Cooley photo system that actually was put on the air for a while. But it was really well understood what the requirements were for television. You had to divide an image into a number of components, convert each component into an electric signal, send the signals to another location by wire or wireless, convert the electrical signals back to image components, and reassemble the image components in the proper position, and then repeat those steps rapidly so the human eye sees a moving image. And Alexander Bain's 1842 invention earned him a posthumous Emmy Award in 2016 for the first concept of breaking an image down to its components. Now you can see up on top, he had a line for a sync signal, which was locking two pendulums together. And then there was a photochemically treated paper that they would read on one side, and then it could, with a battery, like burn an image onto the other side. So even though it was never really produced, he was recognized for having the first system of really breaking it down and sending it in 1842. Soon selenium was, when selenium was discovered in 1817, but it was decades later that this man, Willoughby Smith, utilized its property as a semiconductor in his system for testing underwater telegraph cables. But he soon found out that the selenium behaved erratically, and it was becoming more and more conductive when it was exposed to light. So he kept investigating this, and he developed the selenium cell. And you can see here the response curve of it. But he was also one to receive another posthumous Emmy in 2017 for what was called the concept of optoelectric transconduction, or taking light and converting it to an electrical signal. And it would be others that would use this device in these early televisions. But there's also systems developed to send a still image. This one was an early system by a Professor Korn, and it was called the compensated selenium system. And the way it worked was light at N1 was passed through a translucent image to be reflected by P1 and hitting selenium cell S1. And that cylinder was advanced by a motor or hand crank down there at K on a screw, so it would be advanced as time went on. And then eventually it came across, and between the two magnets, M, they had what was a vibrating reed that was based on the amount of current going through it, and then the light source N2 would go and eventually expose that cylinder C2. And the end result was he was able to produce a very nice picture that's in, let's see what year, 1907. That picture on the bottom was sent from London to Paris. And that's Professor Korn at the top. And all I can imagine there is, since he didn't have a sync signal, he had someone on the other line saying, "Start now." And then the cylinder would start to move, and they would get their image. But the slow, nonlinear response of selenium as a photoresistor could be adapted for these still images, but inventors were going to find it pretty hard to use selenium with that slow fade back at dark. You could see the time in seconds really starts to build up. The next development was from Paul Nipkow. He invents that famous disc that divides the light with a scanning spot. And the very simple explanation of how it works, the light going through the transmitter disc, picked up by the selenium cell and converted to light, and then reproducing an image. I was surprised to find out that late in his life, Nipkow, 72 years old, spoke to a reporter about the Christmas Eve in 1883, when a poor and hungry inventor, he was working on ideas for what he called his favorite problem, the televisor. And he said that as soon as the idea hit him, he jumped up and danced around the room like one possessed, so that his landlady came full of terror, fearing something had happened to him. But what he said that happened to him was just a beautiful thing. It was the best Christmas he had. He was no longer felt hungry. He felt rich and happy. Of course, I don't know that he ever got rich, but he at least, his spirit was enriched by his idea coming through. The neon tube was the next advance in producing the light to be used in producing an image. This is the phases of construction of one of these. You've probably seen the examples of these tubes over in the museum. And they have a very rapid response from a signal coming in to the light coming on. And if you looked at one of the working ones we had on last night, they're very bright. But putting together a system that utilized all these devices was first done by John Logie Baird, and he's credited with creating the first moving electric image. This is one of his early devices. It's called the Double 8. There's 2 spirals of 8 lenses on that last disc that he's moving. The disc before that, with the slots on it, is one thing that they learned to help with those selenium cells. Is instead of a steady light, they chopped up the light so that there was like you were using the better part of that response curve of selenium. It was cutting off earlier so you didn't have that long, slow drop off in the signal. And this is what's credited as the first television photograph from the Baird system. Contrary to the American scanning disc sets, you can see its vertical scanning lines on these. And Baird went on to produce many firsts, including color images, and this one is a 3D viewer. So it's a system there's 2 pieces to look in, and each had a separate spiral. So he created what was a 3D looking image. And a lot of his different firsts, he was one of the first to transmit to a ship, were all things that really appear more to be publicity stunts as he tried to raise money by getting new investors as he would get press coverage of these events. This is a young C. Francis Jenkins, shown with his first big invention, the Fantascope. This invention was an early movie projector, and unfortunately for Jenkins, his partner sold out the invention to Edison, and it solved some of Edison's problems with his projector, the kinetoscope, and so the Fantascope went away, and Jenkins was basically left to start over, hopefully without a partner. But his first invention in the way of television came with this prismatic disc, and the way this is built, if you look at the way it's cut out of glass, it starts with a thicker piece, and as you go around, it gradually diminishes in size. And what happens is as the light passes through that, with a prismatic effect, it deflects, the rate of deflection changes as the wheel turns. So a single beam of light going through there would get a deflection, and if you put your beam of light through the top, it would be horizontal, or the bottom horizontal, the sides vertical. And this was one of his early pieces to use a disc was to scan motion picture film, where the vertical motion was by the hand crank, and then the horizontal motion was by the disc. He also had big apparatus for doing still images. This one used multiple discs, and the motor is running one of those things to chop up the light so that the selenium cell would work better. And he got very good images. This is a still image sent through that system. But again, he wanted to do moving television, and his invention for that was this scanning drum. So the neon tube would have been placed in the center of the drum, and the light from the tube, as the drum turned, went through these quartz rods, kind of like a early idea of fiber optics, to light up the respective holes on the drum. This is a diagram of how that system worked, and you can see that in this one, the neon tube all the way on the right actually had 4 elements in it, and then like in a car distributor on the far left, there's the contacts to engage each part of the neon tube as it was needed. And that neon tube would be slid into the cylinder, the light reflected up the top and magnified for the viewer. This is a picture of, these are pretty rare, the 4-element neon tubes. And this is Jenkins with that set. I've never seen anything that these were actually produced for sale, or if they were, none have survived that I know about. But he did make presentations to the press and to the public, and that's Jenkins holding one of those tubes on the left. And it picked up coverage. This is the radio news coverage of that new product that would be coming out, because certainly now television was just around the corner.
What year is that, Mike?
This would be around, I think 27. Is the date on that radio news? I think it's 27. Now, in order to improve the viewer's ability to follow a story, because if you looked at any of the scanning discs here, it'd be about impossible. But he found it best to use what they called shadow movies. So that the performers are backlit. The woman there is holding the what they call a transmitter. They didn't call it a camera, and that's Jenkins directing the action. And this is another one he made with the audio receiver built into it, but again, it's one I've only seen in pictures. The next development to improve these televisions was the photoelectric cell. They used a photoemissive coating inside of the bulb, and as DC voltage is applied to the anode, the incoming light produces a small current. These cells were an improvement in sensitivity with a faster and more linear response, certainly than the selenium cells. And to get more current, the amount of current was is in microamps. They would use more tubes and bigger tubes. So some of them had an array of maybe 6 big tubes around the reflectors. So in 1923, Bell Labs decides to investigate television to keep the Bell system abreast of the great advances in the art of television. And this assignment went to this Dr. Herbert Ives, who became very famous for his work. And he was given as opposed to the independent inventors, he had a sizable staff and a sizable budget. And he got some pretty good results. This is one of the first times I used it to just transmit photographs from Cleveland to New York. This is at the funeral of President Harding. That's President Coolidge and his wife. And they sent a total of 15 photographs, and it only took 2 hours. There'd be a lot of flicker if you tried to make a motion picture out of that. And this describes one of the two-way telephone setups. So this man with the microphone is in front of the transmitter that would be scanning him. You can see a light source back there, and the scanning disc is in there too. And then the equipment to send it down the line. And one of the first celebrities that was Secretary Hoover making a video phone call. They also made for a number of people to view an image what they called the neon tube grid receiver. And what was in that was really pretty clever. It was a continuous neon tube with only one of the elements of the spiral conductor you can see in there going through the glass tube. And then outside of the tube were these foil strips. And as a foil strip got some voltage applied to it, the neon light would flicker through the glass at that point. I don't know if you look at a regular neon lamp, if you could imagine only one element being inside, one element being outside, and you would still get a glow of neon on the inside. So this is an enlarged section of it. You could see it zigzagging up and down. And then at the back of the grid, you can see they had to make a few connections. And each connection for one of those foil strips went to this spinning wheel, and that was spun by that big motor back there. this is only in grayscale, but it really looks like all those wires are the same color, so I don't know how they could have figured anything out there. But with this success, television was definitely now a reality. The Secretary Hoover's picture, this made the newspapers, and again, television must be just around the corner. And even though they weren't promoting its use, they were doing demonstrations to keep the Bell Labs work in the news. So what you could get was an invitation to a television demonstration where you would be on a two-way telephone video call with another person. So you would be sent to one AT&T location, your friend would go to another location, and you would video chat through their system. This was in February 1931. One of the next famous inventors to get involved in television was Ernst Alexanderson, who was famous for his Alexanderson alternator in the early days of radio. He was what his family described as a classic absent-minded professor that his daughter said that she could pass him walking on the street and say hello to him, and he wouldn't know who she was, and they would just both keep on walking. And in this picture, he's demonstrating the set to his family. You could see on the very tiny screen they're all looking into on the top there, and that's a radio, like a 104 speaker system next to it. When he was giving one of these big demonstrations for a lot of dignitaries, he was very nervous and couldn't get it to come on. And finally, his wife came over to him and said, "You have to plug it into the wall first." So one of the things that Alexanderson investigated was other inventions. He actually took a trip to Europe on GE's expenses to find out about some of these things. And one of them was the mirrored scanning wheel. I've got a little blow up. You can see the way it works is the angle of each mirror is tilted slightly. As it goes totally around, it comes back to a starting point. And this Professor Wheeler was the inventor of this. And his work was taken up by this Professor Carolus in the 1920s. And he's the one that Alexanderson met with, and he actually came back here to work on it with him. And they also used another device that was going to pass a lot more light through, called a Kerr cell. And what they had discovered was that with the right chemical solution, you could apply a voltage to this liquid cell, and the polarization of the light going through would be shifted. And you can see on this graph, the amount of light intensity going through at 300 volts would be a lot less. 425, you're about mid-range, and 550, full amount. So by just applying that range of voltages, they could make this work like a valve, letting more or less light through. And then there would also be these prisms that would work with the polarization of the light coming through to help it act as a valve. The system that Alexanderson started to use, they decided that they projected through 7 spots of light, all modulated the same way, but they thought the presentation was better, that it didn't appear like you had really thick scanning lines. So the 7 spots is just for effect. But then it would go through these lenses and get projected through the mirrored drum. This is Alexanderson demonstrating it, pointing at the spot. But they did a lot of demonstrations. They'd have an orchestra playing, and you could see the conductor on the rear projected screen. And down below there is, it's better in this picture, that's Alexanderson with the big flying spot scanner. They also had a first at GE where they broadcast a play through WGY. This is called The Queen's Messenger, and it was chosen because the entire play took place at that one table over there, so they didn't have to move around much. And they had one of the that octagonal shaped box on that one is GE's Octagon receiver. That was their monitor to see what was actually happening. And you can see the man with the camera in the back with the light on it. There's one of these sets that GE made that still exists in a museum, and Steve has a replica here in the lobby when you come in. So they even were confident enough that they were going to televise this speech of Alfred E. Smith accepting the presidential nomination outdoors. It was going to be broadcast with their flying spot scanner. And they did a test. Everything worked out okay. The spot must have been pretty darn bright in regular daylight to still be able to produce a signal. And then the actual event came on, and there were also newsreel cameras there. And the newsreel people turned on their own floodlights. Well, that kind of wiped out the flying spot. So anyone who did tune in to WGY that day got a blank screen in the audio. At the same time, this is Frank Conrad at KDKA, the Westinghouse engineer who started the earliest broadcasting station. And he got involved with an idea for radio movies. At the same time, Zworykin was working at Westinghouse in Pittsburgh, and he was working on, and he did actually tests with a CRT receiver and a scanning disc transmitter. But he must have never gotten past the earliest of testing stages because there wasn't much, and no photographs about that. But what Conrad was doing, used this system with a scanning disc to scan movie film. And he had a light source that L1 would be focused on scanning disc D. And then they only scanned it in the vertical direction, passed through L2, and then the horizontal direction was accomplished by the film moving. And then the light that passed through the film was picked up by the photocell in P rather. There was big announcements of that. There were articles in Radio News, but nobody ever saw anything about it actually getting on the air. Then Jenkins was starting to produce more and more sets for the amateur use that was going on, people building home units. This is one of mine, and you could see I happened to get it lined up just enough that it magnified the spots, the light coming through. And they also made some more sophisticated sets. This one's on display, a Model 201. It's at the AWA Museum. It uses a scanning drum, neon tube in the center, and then to make the drum compact, it has this obscuring disc that they called it, that would be synchronized by sharing the same shaft geared down from the motor, moving the drum, so that at any time, if you look at the 4 dots that are in the rectangle in the center, that was the imaging area. So at any time, 3 of them were blocked by the obscuring disc, and only the proper one for that frame went through. If you look at the way it has 3 there, they were using 45-line triple interlaced. So that's how they were accomplishing that. And they got some promotions. This was in 1927, a demonstration. And again, they were transmitting, but there was no great interest. But this story reported in the November-December 31 television news shows something that I hadn't heard about before, how there was a lot of activity in Chicago with mechanical televisions. And you can see some of the sets that were being produced in the area. And as I looked into this, I found out that television in Chicago never would have happened if it wasn't for William Randolph Hearst, a confident and enthusiastic teenage inventor, and Eskimo pies. So as I dug a little more into this, the inventor was Ulysses Sanabria, who you can find a lot of things about him. But as a very young, enthusiastic inventor, he claimed that someday he was going to produce a television set. And he also made these claims to impress young ladies. Now, what came first, the idea of how he'd make a television or impressing the young ladies, I couldn't find any documentation on that. And then Hearst heard about this young inventor and funded his startup and gave him space in his building. Whether he just said this is a long shot and if this takes off, I'll have an inside track, but and maybe part of his publishing empire would have to move to an early version of CNN or something, but he funded a lot of it, and then at the time as home refrigeration was starting to come around, Eskimo pies took off, and the guys who were running that business were making so much money that they decided to invest in something a little risky, and they formed the Western Television Company. And so those three, utilizing Sanabria inventions. So Randolph Hearst enabled Sanabria and Sanabria selling his patents and production through Western. And Sanabria himself worked on large screen projections, and he was able to get a high intensity light by, there's not much information about it, but they called it a Taylor gas arc tube, and it used some kind of a ball of flame tube inside of that they could modulate. But this model, the Western Visionette that there is in the museum, was probably the most popular of their products. It was very simple, just the disc and a motor to attach to and a holder for the neon tube, and then you'd have to attach it to your own radio. And according to the database, I don't know, it might have been updated, but 28 of these surviving, maybe that was number 29 that's in the auction, is about the high point for any of the surviving mechanical sets. And then the Western / Echophone company also went on to produce a very neat tabletop radio, a television monitor that is both available as this standalone, just the video receiver, and the double one that's the Empire State that's over in the museum. But this was state of the art now for 1932 and 33. And it showed that large screen for the whole family to view. Brighter images using this crater tube, and we'll get into the individual details, but the way the whole large screen thing worked was it was now a rear projection. You weren't looking through a magnifier. So that frosted glass is actually, the whole image is going to be on there, so more than one could watch at a time. This is the unit broken down. And I was talking to people last night about what the scanning disc would have looked like. So for triple interlaced, you can see there's 3 slightly different spirals, and each of these spirals has a lens in it. The brighter image part came from this new crater tube, which still took the idea of a neon lamp, but they found that if they concentrated the part that would light up to a very small area, that I guess was the crater, and then also heated it with a heating element, that they got a very bright light, and that's what was projected through each lens. And this is the assembly on the receiver chassis. The motor was improved by having this shaft go through that you could adjust it to get the framing and a steadier image on it. It didn't jump around as much. And a sensitive receiver that used the screen grid tubes that were just coming out at the time. And part of the reason that Western and was combined with Echophone is the one who was selling home radios, and that was how they could make this receiver, because Echophone had the RCA license. And you can see on the bottom of the set the number of patents that come with the RCA license. And there's also 8 or 9 Hazeltine patents that had to be licensed to build these. This serial number 8838, I think maybe they started with serial number 8800 or something, because there just aren't a lot of these. This is the console in the museum. So this had the audio section down the bottom, speaker way down the bottom, and the television receiver on the top. One of the young engineers, because in this 1932 little burst of activity in mechanical television, was Alan Dumont. And he worked for Globe at first. This was what he was talking about in this article that he wrote, and then went on to work for the Jenkins Company. Was folded into DeForest, who then promptly went bankrupt, and that was the end of the Jenkins televisions. But this is one that would have been from the vintage that Dumont would have worked on, and this used that the crater tube would be down the bottom towards the center, projecting through those lenses and then reflecting off the back mirror onto the front face. The highest resolution any companies were putting out at the time would have been in that area of 48 or 60 lines. So this is another one of the young inventors at the time, Hollis Baird, no relation to the English Baird. His company, Shortwave and Television Corporation, was in Boston, and they produced a number of models of scanning drum televisions. Now, if you look at some of the scanning disc images, you have a keystoning problem. And the reason to go to the drum was to get away from keystoning. But this is in my collection. It's a very well built. There's an outer shell to hold the drum. The drum spins on the inside. The neon tube is down from the top and viewing from the front. This is another one of their models that used a scanning drum, very, very narrow though. And in this picture, the holes are so small you can't even see that they're there in this picture. And they marketed a lot of their stuff through Kresge, the 5 and 10 kind of store. And they were in the catalogs for that year. That's the receiver. There's one of the receivers down in the museum. And the prices were also dropping. They started with kits for $60, and later they were reduced to as low as $39. That's the Globe one. And this is another oddball one that I found. It was made called the Televisor, where so you wouldn't have that big cabinet for the disc that had a disc down low spinning and the light reflected through it. Pilot, who entered the TV market in New York because of an association with WRNY, which Hugo Gernsback backed, which was transmitting. So they were building the sets for them, and I don't know of any of those that survived. And this is their the CBS television studio in 1930 in New York, where they were experimenting with scanning disc television. And a lot of the effort was from people reading the magazines was to build your own. Hopefully you would get someone who could you could buy the disc from, because if you think about it, if you're going to have 48 lines in a 1-inch area of the disc, each hole you're making is going to be 1/48 of an inch, and you've got to precisely line it up, index it down enough for the next spot coming down, which it's hard to imagine someone doing that at home. And then they also had the worry of the different formats that were out there. This cartoon shows the troubles experimenters would have, because you'd have to build one of every kind for everyone who was transmitting if you wanted to get all the shows that were out there. One company, Davin, made a triple disc. So it had 3 formats on the same disc, and you would move that slide up and down to take your viewing port to the right part on the disc. But all of this showed that if you were going to try to watch TV, you still had to make a lot of choices of who would be in your area and what format they would have, anywhere from 24 lines, 30 lines, 36, 45 triple interlaced, 48, 60, and then even an 80 and 96 out in California. And from that same home experimenter, there were guides in television news as to everything to try when your images are all coming out wrong, flipped upside down, you name it. As this was trying to take off, this company called Seall built the Seall, a television manufacturing company of America. They rented space on Broadway in a building and had free demonstrations of all their models, kept it going for months, and would try to find prospective buyers for when they would go into production, and they never came up with enough buyers to go into production, so it just faded away. So what you would get if you did all that to build your own television receiver was still not too impressive. If this guy's trying to watch almost anything through that little hole, he's going to have a tough day. They did publish schedules. This is probably the peak of everything in around 32, as it was starting to lose its momentum, because you're in the Depression and you're not getting any programming really worthwhile, but you still had to go through to pick your station, pick if it's a single spiral, 48 holes, how many RPMs you had to turn, and what time they would be on. So to find anything really good out of that would be really a tough job. So as part of what you could see happening at the end of mechanical TV, Jenkins would try to encourage his viewers to write in, giving him a program report, and he actually published in his book all of the responses he got, and he only got 30 names. So his shadow movies did not exactly take hold. In that 1933 interview, Paul Nipkow was asked about the progress on mechanical television using his discs. And he said, if I'm not mistaken, the Braun tube, with the long glass tube with a deflective cathode ray, has the most prospect for realization, so the inventor was giving up too. Alex Anderson wrote an article in February 27 issue of Radio News that, based on his research, he could see that he could produce a really quality image. But if he was to try to do that at 16 frames per second, he'd have to improve the scanning time to 1/1000th of what he was able to do with his hardware. So he was giving up that his hardware wasn't going to do the job. He did admit that he thought there might be some useful service if all you wanted to do was get an image of your buddy who you already recognized and say, yep, that's him, and he's waving to me. But he didn't see much beyond that. This is kind of a sad thing. In 32, Philo Farnsworth took his electronic equipment to England for a demonstration to the Baird Corporation. And Farnsworth's wife was there, and she remembers when Baird came through the door and saw the whole display set up, he just didn't say a word to anybody, just stared at it for a while, and then just finally broke the spell and walked out of the room. And that they all realized that that man was seeing the end of his beloved scanning disc, that electronic was going to be doing the job. I found an interview with an RCA engineer, Ted Smith, who was responsible for the construction of the RCA mechanical station. And he told this story of setting up a demonstration for VIPs in a theater in Manhattan. They got their best equipment, set it all up. They did a great demonstration. Sarnoff was the main VIP, and he and his crew watched the people watching the demonstration. It went perfectly, and when it ended, they saw the faces on the people as they were leaving. They took their equipment, put it out in the dumpster. So really, if you think about it, as electronic television was leading the way, none of these companies could really compete against RCA. This is a breakdown of how much they had put in by this time period. This would be late 30s, that they had close to 10 million getting invested. And if you were an RCA license holder, like a company like that Western had to be, why go and do your own research? Because with your license, you got all the information on what RCA was doing, and they would be very happy to have you build electronic TVs with their license. So as the electronic sets came in, the field tests were going on too. This is an early one in 32 field test receiver on the left. That's Darrell Hawks. and an RR359 field test in an engineer's home. And when you look at the comparison of a 60-line scanning disk to 120-line on a CRT, especially with the little bit of blending you get from the phosphors on the screen, there's really no comparison. If anyone looked at the two, you were not going to buy the scanning disk television. So Felix was happy, and as I was doing this research, as happens in many a bad science fiction movie, myself and my assistant, Lila, that's her on the left, we decided to experiment on ourselves. So we soon found we were leaving the digital world and were soon trapped, falling deeper and deeper into a virtual analog abyss. And we tried to move around in a 45-line, triple interlaced resolution world, and before we got permanently trapped in this quagmire, we were able to escape from the lens of our 45-line Western Visionette. And then that's us just before we escaped. Well, thanks for watching. And I guess lunch is served.